Okay, we'll do set B here, and the first one we'll do is SiO2. Okay, SiO2. All right, so the question that you guys want to ask, or we ask ourselves, is what is silicon happy at, Si? So if we look at it in our periodic table, it's right underneath carbon. And carbon loves 4. Okay, it loves 4, undoubtedly. So silicon will also love 4. So silicon is happy at 4. Okay. What is oxygen happy at?
6.
Yes, 4, 5, and 6. Okay, but we have 2. So we have 12 oxygens. I'm sorry, 12 electrons. So how many valence electrons? 4 plus 12 is 16. So we need to get 16 valence electrons around SiO2. So how will we do this? Okay. So I'm going to make silicon the center atom, and then what will be bound to it? Okay, remember, silicon likes 4. So I'll put a double bond here, I'll put a double bond here. Okay, this is how I'll get 4. 1, 2, 3, 4. All right, let's do our electron count. 1, 2, 3, 4, 5, 6, 7, 8. Okay, where will 9, 10, 11, and 12 go? 9, 10, 11, 12. Where will 13, 14, 15, 16 go? 13, 14, 15, 16. Okay, so that is how silicon dioxide is. That is its Lewis structure. Let's do the octet rule and formal charge. Okay, octet rule for this silicon: 1, 2, 3, 4, 5, 6, 7, 8. Okay, everyone good? What about formal charge? Count with me. 1, 2, 3, 4. What is silicon happy at? 4. 4 minus 4 is 0. Okay, let's do the oxygens. Okay, octet rule. Count with me. 1, 2, 3, 4, 5, 6, 7, 8. That's octet. 5, 6, 7, 8. So octet rule is satisfied. What about formal charge? Okay, count with me. 1, 2, 3, 4, 5. This is formal charge. 5, 6. What is oxygen happy at? 6. What's 6 minus 6? 0. Okay, so the formal charge on that is 0. Same thing with that oxygen. Okay, so how many bonding and how many lone pairs on the central atom? I think I have that sheet. 2 bonding, 0 lone pairs. Yeah, 2 bonding, 0 lone pairs. Well, I should. Yeah, I got it. You keep it. Okay. I got it. Okay, 2 bonding, 0 lone pairs. So 2 bonds and no lone pairs. This is linear. Okay, straight line. Okay, 180 degrees bond angle. So if we're going to sketch this in 3 dimensions, the 2 bonds we will use for sketch is dash and wedge. Okay, so just the same thing because it's planar. Okay, it's planar. The electron pair geometry and the linear molecular geometry are the same, and that is linear. Okay, because there are no lone pairs, it's linear. And what is the central atom hybridization? How will we get to 2? We'll take 1 from S, and how many from P? 1 from S, and how many from P? What's 2 plus 0? 2 plus 0 is 2.
3.
What's the hybridization? Now I'm confused. This would be an sp hybridized silicon. Yes, okay. We don't say P1 or S1. We just say S and P. So this is an sp hybridized silicon. Do you see this, Amy? 2 bonds, 0 lone pairs. 2 plus 0 is 2. So to get to 2, we will take 1 from S and then 1 from P. So this is an sp hybridized central atom, and that central atom is silicon. Okay, is this polar or non-polar? Okay, so this oxygen is electronegative, so it's going to pull this way. The oxygen on the other end will do the exact same thing. It's going to pull that way. Okay, I want to try to tell you guys that the arrows will cancel each other out. When the arrows cancel each other out, what will this be, polar or non-polar? Okay, non-polar. Right, so that is our first one, SiO2. Okay, shall we go to the next one? All right, we've got 9 more of these to go. So I'll have this available online when this lecture is over. If you're behind, you can just check the canvas for the video. Next one, SiO3 minus 2. Okay, let's go ahead and do that. Okay. All right, so what is silicon happy at? Okay, it's right below oxygen, so it's happy at 4. Okay, what is oxygen happy at? 6, but we have 3 of those, so that's 18. Okay, what does that minus 2 mean? That minus 2, did we gain 2 electrons or lose 2 electrons? Okay, that minus 2 means we have taken 2 electrons. Only then can we become minus 2, when we gain 2 electrons. Okay, so total valence electrons is 24. That we need to fill around SiO2, or SiO3, sorry. All right, so let's make silicon our central atom. Let's make silicon our central atom. And does anybody remember in this morning's class about oxygen? How can we get it to minus 1 formal charge? Okay. If you take a single bond with an oxygen and put 3 lone pairs, okay, that will give it a minus formal charge. See? 1, 2, 3, 4, 5, 6, 7. What is oxygen happy at? 6. What is 6 minus 7? -1. So there's our first -1. What about our next -1? How will we... Let's do the same thing, yes. Okay. 2, 3, 4, 5, 6. Be -1. Okay. And how will we make... So the total charge is what now, Jack? Is it minus 2? With our minus 2? How will we get to 4 then for the silicon? 1, 2, and we'll make a double bond with the oxygen. And if you remember from this morning's class, if you have a double bond with an oxygen, that is 2 lone pairs. And what's the formal charge on that? 0, very good. 1, 2, 3, 4, 5, 6. Okay, what is oxygen happy at? 6. What's 6 minus 6? 0. Okay. Is there another way to draw this? Okay. This is a little tricky, but I'd like to tell you there's another way to draw this here. Okay. See how I drew the double bond down? How else could I draw that double bond? That is correct. Okay. Okay, so there's my -2 from SiO3 minus 2. But I just arbitrarily chose the bottom oxygen to have the double bond. I could also, just as likely, have this left oxygen have it. So the way you do that is, I'm going to take this pair of electrons, move it here. I'm going to kick this pair of electrons and move it down. Okay? So what will that be? O double bond with my Si. Okay, this stays the same. And this now has my negative. Okay, there's my -2. Anything else that you can see here? I have my double bond at the bottom. I have it at this left oxygen. Where else could I have it? Just as much or just as equally? Okay, you can have it to the rightmost oxygen. Here's how we can do that. Okay, I'll put this here. No, I'm sorry. I already have the double bond there. Never mind. I'll put this here, and I'll kick that out there. Okay? See that? I'll put this here, kick that out there, and now my double bond is on this rightmost oxygen. So there's actually 3 answers to this. Okay, this is called resonance. Okay, resonance structures. This makes this molecule very stable. Okay, resonance. We'll talk about resonance in the Thursday lecture. Okay, but resonance. Okay, this is basically more than one representation of the structure. Okay, so it's not this is the one structure, it's not this is not one structure, it's not this one structure, it's all 3. Okay, all 3. Okay, and this double bond is delocalized. It's shared across these 3 oxygens. Think of a bee buzzing around. Buzz, 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 buzz. That double bond is buzzing around. It's delocalized. So another reason why these types of resonance structures are so stable. Okay, very stable. Also, that negative charge is shared equally. The -2 charges are shared equally across the 3 oxygen atoms. Okay, so resonance is a very nice thing. We'll talk about that on Thursday's class. So there is a resonance here. How many bonds and how many lone pairs? Okay, 3 bonds, 0 lone pairs on the central silicon. And what's 3 and 0? Okay, 3 and 0 is going to be trigonal planar. Okay, it's the formaldehyde example, just like the formaldehyde example. Okay, because there are no lone pairs, these are equal, same. If there are lone pairs, things will get distorted. So how will we do this? I'm going to do it like this, okay? So I will not test you on it on the exam, but that resonance kind of tells you that that -2 and that double bond is shared equally, okay? Across these 3 oxygens. Because of the resonance. In some textbooks we'll do, I can also put a negative here, but it's not it's -2, not -3. So we'll just do that there. Just put a big -2 here. Okay. So it's just basically saying that this double bond is shared equally across all 3 oxygens. Okay. So some textbooks will do it like that. Okay. I will not ask you like this on the test, but if on the test I'll just draw it like this. Okay, but this is trigonal planar. Okay, trigonal planar. Or if you want, you can turn it in like this. Realizing the -2 is shared equally across all 3 oxygens, and realizing this double bond, because of resonance, is shared across all 3 oxygens. That is what I wanted to depict here. Okay, so it's kind of shared. So for testing purposes, it's going to be like this. But if you want to draw a hybrid, some textbooks will draw it as a hybrid like this. Okay. All right, what is the central atom hybridization?
SP2.
This is an sp2 hybridized silicon. Very good. Okay, is this polar or non-polar? Okay, what do you guys think? Polar or non-polar? So we got this oxygen kind of pulling this way, this oxygen kind of pulling that way. If we sum up these arrows, they're going to pull up. Okay, just summing those two, the sum. And then this oxygen is pulling down, which will cancel out the sum of that one pulling up. So I'm going to go with polar. I'm going to go with non-polar on this one. Okay, do you see this? Okay, at this angle, which is 120 degrees, it's going that way. This angle, it's going that way. If you add this arrow and this arrow, if you add those two vectors, it's actually going to go up. And that's going to balance out the oxygen that's pulling down. Okay, so the sum of these two at an angle is up, which cancels out with the oxygen pulling down. This is why it's non-polar. Okay. Alright, so this one here is a good example of resonance, which we'll talk about again later in the course. Alright, shall we move on to number 3? Yes? Okay. Any objections? Number 3 is CI4, carbon iodide. Okay, so CI4. Okay, how will we draw this? What is carbon happy at? 4. What is iodine happy at? The halogen. 7. How many iodines do we have? 4, so we need to get 32 valence electrons around CI4, carbon tetraiodide, I think we call this. So what will be our central atom? Okay, carbon, and then we'll have an I here, I here, I here, and an I here. Okay. Let's fill out the rest with electrons, realizing we need to be at 32. We need to be at 32. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Okay, it works out nicely. Okay, 32 valence electrons. So how many bonding and how many lone pairs? So here's another thing I want to tell you guys. Okay, if you have a halogen, okay, I'll call the halogen X. The halogen will always have 3 lone pairs. X is equal to a halogen. Okay, there's no double bonds because that's going to mess up your formal charge. Okay, so 1, 2, 3, 4, 5, 6, 7. What is halogen happy at? Chlorine, bromine, fluorine. Happy at 7. 7 minus 7, 0. Okay. All right, how many bonding and how many lone pairs? Central atom carbon, 1, 2, 3, 4. 4 bonding, how many lone pairs? 0. 4 bonding, 0 lone pairs. What's 4 bonding, 0 lone pairs? Okay, what we did in class this morning. Okay, 4 bonding, 0 lone pairs. Tetrahedral, tetrahedral. So this is how we'll draw a tetrahedral. Okay, one of them here. One of the I substituent means an outer atom, is at a 109.5 degree angle. We'll have the other I coming out towards you guys. And then we'll have another I coming back. Okay, so this is called a wedge, and that's called a dash. This should all look like a tetrahedron, okay, if you connect the centers of the atom. Okay, if you connect the centers, it looks like a nice tetrahedron. All right, how will we get to 4 and 0? Okay, how many bonds and how many lone pairs? 4 bonds, 0 lone pairs. And what is that? How many S's and how many P's will get us 4? So this would be an S, P, how many P's? Okay, this is sp3 hybridized carbon, sp3. Okay, we get 1 from S and 3 from P. Okay, P only has 3. So this is.
I'm sorry, going back to that next square over, is that an H over that I?
What?
I think you just wrote his eye at an angle
Oh, okay.
in the second box.
Second
Your
box.
eye is an H.
Oh, it should be an I.
Yeah, okay, okay.
Yeah. It's an I. It's CI4. Okay. All right, so this is an sp3 hybridized carbon. All right, and what is the molecular geometry? And the electron pair geometry, they're going to be one and the same, and that's going to be tetrahedral, okay, because there's no lone pairs. And is this polar or nonpolar? Okay, last question before we move on. Okay, so this I will pull, this I will pull, they cancel. Okay, this I will pull, this I will pull, they cancel, and I'm going to say this is nonpolar. Nonpolar. Okay, move on to number 4 here. Okay, 7 more of these to go. Okay, NF3, NF3, okay, nitrogen trifluoride. Right, what is nitrogen happy at? 5. What is fluorine happy at? Okay, but we got 3 of those, so we got to get 26. Okay, valence electrons around NF3. So let's make nitrogen our central atom. Okay, nitrogen. We'll do 1F here, 1F here, and 1F here. Okay. So remember, halogens will have 3 lone pairs. Okay, this is important. This is just something you need to keep in the back of your mind. These halogens will have 3 lone pairs. So it's going to be 1, 2, 3, 4, 5, 6. Let's go to 26. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Where will 25 and 26 go? On the nitrogen. Good job. Okay. They'll go on the nitrogen. All right, let's do the formal charge of this nitrogen. 1, 2, 3, 4, 5. What is nitrogen happy at? 5. 5 minus 5 is 0. Let's do the octet rule for this nitrogen. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's do the exact same thing for the fluorines. Let's do the formal charge for the fluorines. Okay, ready? Count with me. 1, 2, 3, 4, 5, 6, 7. What's fluorine happy at? 7. Fluorine happy at 7. What's 7 minus 7? 0. So the formal charge of that fluorine is 0. Okay, what about the octet rule for this fluorine? 1, 2, 3, 4, 5, 6, 7, 8. The octet rule is satisfied. All right, how many bonding and how many lone pairs? 1 bond, 2 bond, 3 bond. So we got 3 bonds and how many lone pairs? 1. So what's 3 bonds and 1 lone pair? So this is how you read it here. So we got 4 bonding, and out of those 4 bonding, how many is a lone pair? Okay, 1. Okay, so we got 4 bonding, and then we got 1 lone pair. So 4 bonding, 1 lone pair is trigonal pyramidal. That is the molecular geometry. Okay. The electron pair geometry is tetrahedral, but we removed 1 outer atom and replaced it with a lone pair. That lone pair made this not tetrahedral. That lone pair made it trigonal pyramidal. So this is the molecular geometry. You want this, Melissa?
Do you need it for the rest?
No. I don't need it. Let's take it. Okay. That's over here. All right, so this is what happens. 1 lone pair makes it trigonal pyramidal. Okay, lone pairs will distort the structure. This is what I emphasized during this morning's class. Lone pair will take something that's tetrahedral and make it trigonal pyramidal. Take 2 lone pairs, it will take something normally tetrahedral and make it bent. Okay, what molecule was bent in class this morning? Okay, water. Water was bent. The 2 lone pairs do this. Okay, on the water molecule. Okay, so molecular geometry is trigonal pyramidal. Wait, molecular geometry, trigonal pyramidal. Okay, the electron pair geometry is tetrahedral. Okay, if we are going to draw something that is trigonal pyramidal, okay, you can use this as a guide on your exam. Okay, we'll use this as a guide. We'll have 1 fluorine come out towards you, 1 fluorine come out towards you, another fluorine go back, and then that lone pair on the plane, okay, which messes up the structure, distorts it in trigonal pyramidal. Okay, so use this to draw the sketch on the test. All right, so we'll have 1 lone pair on the plane. Okay, coming towards you, coming towards you, coming behind you. Okay, coming towards you, it's called a wedge. Coming behind you, it's called a dash. Okay, so something like this. Okay, I'm not looking for perfection, just, something that you know that we have a wedge that's coming out of the plane of the paper and a dash that's coming behind the plane of the paper. All right, central atom hybridization. Okay, we have 3 bonds, 1 lone pair. 3 plus 1 is 4. This will also be an sp3 hybridized nitrogen. Even with the lone pair, it still will be sp3. This is an sp3 hybridized nitrogen. And then the last thing we want to fill out here is this polar or non-polar. Okay, it's definitely polar. Okay, the electrons are pulling. This fluorine is pulling. We got all sorts of pull. And I really don't see anything counterbalancing it. I don't see anything counterbalancing the arrows. Okay, such that there's no dipole moment or there's no partial anything. So this is a polar molecule. Right. So another thing, if it's nonpolar, there's symmetry. You know, CI4, the previous one, example 3, there's symmetry. Okay, if you look at it in a 3-dimensional thing, there's symmetry. If you look at this, there's some sort of symmetry, the trigonal planar. If you look at this, there's symmetry. In here, the lone pair destroys symmetry. When it destroys symmetry and you got these electronegative elements, it's going to be polar. All right. All right, we did number 4. Let's go ahead and start number 5 here, and that is SEF4. Okay, SEF4. Next on our docket is SEF4, and here it is. Let's go ahead and do that. Okay, what is, or where is selenium? Okay, selenium is under oxygen. And what is oxygen happy at? Carbon happy at 4, nitrogen happy at 5, oxygen's happy at 6. So selenium will also be happy at 6. Halogen's happy at 7. These guys are full at 8. So yes, selenium is happy at 6. Okay, what is fluorine happy at? Okay, fluorine and all the halogens are happy at 7. Okay, so we need to get, what's 28 plus 6? 34 valence electrons, am I right? Yeah. Right, so I'm going to have selenium as my central atom, and then I'll have my 4 fluorines. 1, 2, 3, 4. Okay, what did we say about halogens? How many lone pairs are around the atom? How many lone pairs? That's total, how many lone pairs? For a total of 6, though. How many lone pairs would that make it? 3. Okay, 3 lone pairs around the halogens. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Say it again.
I said he meant pairs, not individual electrons. That's what I said.
Yes, pairs. 3 lone pairs. Okay, for a total of 6. So you're right, it's 6, but it's 3 lone pairs. Okay, for halogens, you're going to have the 3 lone pairs. All right, we have 34 valence electrons. 6 valence from Se selenium, 28 valence from the fluorine. Let's count. Okay, ready? Count with me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Where will 33 and 34 go? Very good. Around the Se. So that is the structure of what is that? Selenium tetrafluoride. Okay. So, Amy, I'll just pick on you. How many bonds and how many lone pairs? Okay, 1, 2, 3, 4. 4 bonds and how many lone pairs?
1.
4 bonds and 1 lone pair. Okay. So that's a total of 5. Okay. So out of 5, how many lone pairs do we have? Okay, we have a total of 5. 4 plus 1 is 5, right? Out of 5, how many of them are lone pairs?
Sawhorse.
Yes, sawhorse. Okay. I don't know how it's sawhorse. Okay, so how will we draw a sawhorse? Actually, we should make a sawhorse there. Anyways. Okay, I'll have 1 fluorine come out towards you guys. I'll have 1 fluorine go back away from you guys. I'll have 1 fluorine on the plane of the paper. I'll have 1 fluorine on the plane of the paper, and I'll have this lone pair coming out on the plane of the paper. Okay, so this is how I plan to draw it. Okay, so on the exam, I'm just looking for you to do the dash and the wedge. Okay, so SEF4. Okay, for the sawhorse. Okay, I'll have 1 fluorine up, 1 fluorine down, 1 fluorine coming towards you guys, up above the paper, 1 fluorine getting down below the paper, and then 1 pair of electrons on the plane of the paper. So let's draw that in 3D together. Okay, so 1 fluorine up, 1 fluorine down, 1 fluorine coming towards you, 1 fluorine going back away from us, and then 1 electron. Usually they put these electrons in what are called lobes, and 1 lone pair like that. Okay. Let's do this formal charge here just for a second. Let's go back here. Formal charge of the selenium. 1, 2, 3, 4, 5, 6. What is selenium happy at? Same as oxygen. 6. What's 6 minus 6? 0. Formal charge 0. Octet rule. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's okay. Okay, this expanded octet is okay. Okay, the octet rule can have a lot of exceptions. This is one of them. As long as I get my formal charges all to 0, because this whole thing is 0, right? This whole thing is a 0 charge. As long as I get my whole thing minimized, I'm okay. All right, so the molecular geometry is sawhorse. Okay, sawhorse. And the electron pair geometry is trigonal bipyramidal. You see, when we take 5 and we remove 1 and make it a lone pair, it becomes sawhorse. But if we had all 5 atoms, it would be trigonal bipyramidal. And what's the central atom hybridization? P only has 3. Okay, how will we get to 5? Okay, so we take 1 from S. That's 1. We need 5. We can take 3 from P. That's 4. And then where will we go next? D. So this is an sp3 dehybridized S selenium. Okay, is this polar or non-polar? Okay, this pulls, and the net is here. This fluorine pulls up, this fluorine pulls down. This pair of electrons pull, but, you know, this is an electron, so it's a lot more powerful than these two pulls.
Would you consider him a ghost?
What's a ghost?
This looks like a ghost.
This? The
Yeah.
lone pair?
So if he's not there, then I guess you can consider it a ghost, right? You said that-
If it's there, but it's not bound to anything. So I guess you can consider it a ghost, yeah. But this ghost is polar. Okay.
Okay.
Okay, because this a lone pair of electrons are going to pull, and I would say that these two fluorines are not strong enough to cancel out the pull of these electrons. Okay, if we replace that with, let's say, this lone pair of electrons bound to another fluorine, would it be polar or non-polar? Definitely it would be polar, because this pull will cancel out that pull. Okay, so yeah, this is a polar molecule. Okay. This is a much stronger pull than those two. And this is the sum of that angle and that angle. All right. Okay, we got 5 more to go. And let's go with IF5. Okay, so 1, 2, 3, 4, 5. IF5. Okay. Iodine tetrafluoride. Okay, number 6 here. Okay, so what's iodine happy at? 7. What's fluorine happy at? 7. So we need to get 42 valence electrons around IF5. Okay? Okay, so what I'll do is I'll have iodine as my central atom, and I'll bond it with 5 fluorines. Okay. 1, 2, 3, 4, 5. Okay? Okay, what did we say about halogens? How many lone pairs? Or how many total?
3.
3 lone pairs for a total of 6. Very good. Okay, so we'll do that around the outer atoms. All right, so 42. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Where will 41 and 42 go? On the iodine. Very good. 41, 42 on the iodine. Let's do a formal charge thing on this iodine for 1 second here. Okay. Okay, ready? Count with me. 1, 2, 3, 4, 5, 6, 7. What is iodine happy at? 7. What's 7 minus 7? 0. Now this octet is going to be expanded. The iodine. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But that's okay. Okay, that's okay. This is all right. Okay, expanded octet. All right, how many bonding and how many lone pairs? So I'll pick on you again, Amy. Okay, 1, 2, 3, 4, 5. 5 bonding. How many lone pairs? 1. Okay. Total of 6, but out of those 6, 1 of them is a lone pair. So what will that make this? Total of, move it out here. Total of 6. We got total of 6, and out of those 6, how many are lone pairs? 1. So 6 bonding. Out of those, 1 of them is a lone pair. Well, this will be square pyramidal. Okay. It's octahedral, but we removed 1 of them and made it a lone pair. One of them is not bound. That's a lone pair. So the electron pair geometry is octahedral. The molecular geometry is square pyramidal. Okay. That's the power of the lone pair. So let's fill these out here. Octahedral. And this is square pyramidal. Okay, what's the central atom hybridization? How will we get to 6? We'll take 1 from S, 3 from P, that's 4, and then how many from D? 2. So this is an sp3d2 hybridized iodine. Okay. How will we draw this in 3 dimensions? Okay, so on the exam, I'm only looking to see if you use the wedge and the dash somewhat, the proper way. Okay, we'll use this as a guide. Okay. This is IF5. So I'll have my iodine, okay, one of the lone pairs will be on the plane of the paper. Okay, one F will be to the right, one F will be up, one F will be down, one F will be in front of you guys, and one F will be behind you guys. So let's do it like that. Okay, so square pyramid, I'm using this to help me. Okay, one F will be here, one F will be here, one F will be here. Okay, one lone pair, you call it a ghost. Okay, or an electron inside a lobe, or a ghost, will be here. One electron, one fluorine. Will be here, and then one fluorine will be there. Okay, I think that's a good way to write this in 3 dimensions. We can actually build it. We can maybe do that in our lecture. Okay. Okay, is this polar or non-polar? Okay, there's no symmetry in the molecule. Okay, if we bound this with a fluorine, I would say it's non-polar, but there's no symmetry. I'm going to call it polar. Okay, you see that this pole will just, go that way. Okay, so this would be polar. All right, we got 4 more to go. Let's go to 7, 8, 9, 10, and then we're done. CH2F2. Okay, CH2F2. This is easy. Okay, CH2F2. Okay, how will we do CH2F2? Okay, carbon, one hydrogen, one hydrogen, one fluorine, one fluorine. Okay, we can do it that way. Or you can have it in any arrangement. You can have the fluorine up, hydrogen to the side. You can do any arrangements. Okay, but those are called isomers. Okay, probably will not study that, but isomers means that you can have one way, or you can have the fluorine left and right, hydrogens top and bottom. You can have the fluorines top and bottom, hydrogens left and right. Those are called isomers. Right, so this is one way to depict C2H2F2. For our halogens, they get 3 lone pairs around it. And let's make this into a tetrahedron. 4 bonds, 0 lone pairs.
What notes do we have for our test?
That.
Okay.
That thing there. All
So
right.
we'll have to memorize what they're happy and like.
Yes, which is easy. Okay, you just go to the periodic table. This is where they're happy. Okay, we'll focus on this. Okay, hydrogen happy at 1. I'm not really talking about these guys, but because they are metals. And hydrogen happy at 1. So this would be 2. Boron and them all are happy at 3. Carbon happy at 4. Nitrogen happy at 5. Oxygen happy at 6. Fluorine happy at 7. Noble gases happy at 8. So just go 1, even though I'm not talking about this. 1, 2, 3, 4, 5, 6, 7, 8. What the heck? Right, so this is a perfect tetrahedron. Okay, 109.5 degree angles, 4 bonds, 0 lone pairs. 4 bonds, 0 lone pairs make it an sp3, hybridized carbon. Okay, the electron pair geometry and the molecular geometry are tetrahedral. Okay. Okay, is this polar or nonpolar? You would think it's nonpolar the way I drew it, where the fluorines pull, but actually it looks like this, okay, because this is not what it looks like, okay? Actually, it looks like this. This fluorine is pulling, this fluorine is pulling, so there's no counterbalance, okay? There's no symmetry. This is a polar molecule, okay? What if I replace these hydrogens with fluorines? Then what would it be? Then it would be nonpolar, okay? But these fluorines do not cancel each other, okay? Based on the 3D structure, they do not cancel unless I take this hydrogen, replace it with a fluorine, and I take this hydrogen and replace it with a fluorine. Then it would be nonpolar, okay? There's no symmetry, so you want to look for symmetry in the molecule. All right, 8, 9, and 10. Let's go for it. Finish it off. What's 8 here? All right, 8, I'm going to talk about this. It will be on the exam, so we'll just talk about this a little bit. C2F4, okay? C2, what is it? F4. So how would you draw C2F4? Okay, carbon loves 4, and carbon loves to make a bond with another carbon. So how would we do this? A double bond with C, yes. Okay, C. Okay, we'll talk. Okay, double bond with C and then F4. Okay, that's fine. I'll talk about something else later. Okay, C2F4. That's correct. Okay. All right, so this has 2 central carbons. Okay, so this carbon has 3 bonds, 0 lone pairs. That second carbon is 3 bonds, 0 lone pairs. So these are both sp2 carbons. Okay, so we have a trigonal pyramidal for this carbon, and then we have a trigonal pyramidal for that carbon. Okay, 120 degrees. Okay, this is what C2F4 looks like. Okay, 2 sp2 carbons. sp2 carbon here, and an sp2 carbon there. Okay, so I'll just say sp2 carbon plus another sp2 hybridized carbon. All right, what's the electron pair geometry? Okay, 3 bonds, 0 lone pairs. So 3 and 0 will make it trigonal planar. Okay, trigonal planar. Just like formaldehyde in our example in class. Okay, trigonal planar. trigonoplanar? And is this polar or nonpolar? Okay, do you see a symmetry in the molecule? Yes or no? Yes. Okay. If you see a symmetry within the molecule, it's going to be nonpolar. So these fluorine poles will cancel out these fluorine poles. Okay. The way you notice this, it'll be, the way I see it, is with symmetry. Symmetry. All right, 9 and 10, and we are done with the lab. Okay. So 9, and then you make sure you turn in your final lab report also. Okay. C2H4Cl2 is our next one. C2H4Cl2. Go ahead and do that. All right. Okay, so how will we do C2H4Cl2? Okay, so we'll have a carbon here bounded to another carbon. And then we can fill that out with some hydrogens. 1, 2, 3. Maybe I'll do a 4 here, and then we can do a chlorine here. Okay? That's one way to do it. Okay? You can have the chlorines on the first carbon. You can have the chlorines at the top. You can have the chlorines at the bottom. You can have the chlorines left and right. So this is another example where you have a lot of isomers. Okay, isomers. Okay, isomers meaning you can arrange the atoms differently. Okay, isomers. This has two central atoms. Okay, we have this carbon here, which is an sp3. Okay, 4 bonds, 0 lone pairs, and then we have a second sp3 carbon, 4 bonds, 0 lone pairs. So we actually have 2 tetrahedrons joining together. So let me see if I can draw this. Okay, we can draw 1 tetrahedron, but can we draw 2 of them? I'll try. Okay. Something like this, okay? So I'm just trying to draw 2 tetrahedrons together, okay? So however you do it on the exam, it's okay, but we try to get to the point of getting 2 tetrahedral molecules together through this C-C bond. This is sp3, that's also sp3. This is a dash bond. This is a wedge bond, that's a dash. This is on the plane of the paper. Right, we have 2 central atoms. We have 2 sp3s, an sp3 here, sp3 here. So we have an sp3 carbon with another sp3 carbon. Okay, sp3 carbons are tetrahedral. Okay, tetrahedral. There's no lone pair, so it's also tetrahedral for the molecular geometry. And is this polar or nonpolar? Do you see any symmetry in the molecule? Okay, there's no symmetry that could be done in the molecule. Okay, and because there's no symmetry in the molecule, this is going to be polar. Polar. even if I put the Cl here, let's say I put the Cl here and make it one of the isomers, this Cl pull will not counteract or counterbalance that Cl pull. Okay, they don't, because they're just too far away. Okay, so you'll have to look for symmetry. So this would be a polar molecule. Alright, and then finally we have ClF3. Okay, this is our last one, ClF3. Okay, coming back to this one, there's a lot of isomers. And you can put the Cl here, the Cl there, and switch them around. Those are called isomers, but no matter how you switch them around, the Cl poles, the Cl electronegativities will not cancel each other. There's no symmetry within the molecule. Okay, there's no symmetry. Because I see no symmetry, it's a polar molecule. All right, our last one here is ClF3. Okay, what is Cl happy at? Halogen 7. What is fluorine happy at? It as well as a halogen, so 21 plus 7. Okay, we got to get 28 valence electrons around ClF3. All right, so I'm going to put a Cl up front, and I'll do 3 fluorines. Okay, we need to get 28 valence electrons, and how many electrons are going to be around the halogen? 3 lone pairs for a total of 6. All right, so count with me. Okay, let's finish strong. Count with me here. 28. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Where will 25, 26, 27, 28 go? 25, 26, 27, 28. Okay. All right, so we have the central chlorine. We have our central chlorine. How many bonding and how many lone pairs? 3 bonding and how many lone pairs?
2.
Okay, very good. Okay, nice job, Shay. 3 bonding, 2 lone pairs. So, what will that make it? Okay, so 3 bonding, 2 lone pairs, total of 5. Out of these 5, how many are lone pairs? You just mentioned it. Okay, out of these 5 bonding, 2 of them have gone the way of lone pairs. This is T-shaped, okay? It was trigonal pyramidal, but because out of those 5, 3 are bound, 2 have become lone pairs, the distortion of the shape becomes T-shaped. So that's the molecular geometry. It's called T-shaped. T-shaped. The electron pair geometry is trigonal bipyramidal. Pyramidal. And what's the central atom hybridization for 3 plus 2 is 5. So we will take 1 from S, 3 from P, and 1 from D. That's a total of 5. So this is an sp3d hybridized chlorine. Okay. And how will we draw this in 3 dimensions? Okay, so I'm going to use this to help me out here. T-shaped as an example, ClF3. Okay, I'm going to have 1 pair of electrons go to the left, 1 pair of electrons go to the right. I'll have 1 F go up, 1 F go down, and my third F come towards you guys. Okay, So I'm using this to help me make the T shape. So let me just use that to help me out. I'll have one chlorine, and then I'll have one fluorine go up. I'll have one fluorine go down. I'm using this to I'll have one electron left, one electron right, and have one fluorine as a wedge. Okay. One lone pair here. One lone pair there. So that's 1, 2, 2 lone pairs. And here's my third fluorine as a wedge bond. Okay, this is called T-shaped. It looks like a T. Okay. All right, is this polar or non-polar?
Or
I would call it polar. Okay, just the way I drew it. Okay, while these pair of electrons may repel one another, this fluorine and this fluorine may repel. This fluorine pulls kind of out there. So there's they don't cancel each other out. This is a polar molecule. Okay, I don't see any symmetry. Okay, everyone agree? Okay, no symmetry. Okay, these electrons cancel. This fluorine and that fluorine cancel. There's nothing to cancel the pull from this fluorine, one of the fluorines. Again, no symmetry. It's a polar molecule.